There's sort of one paragraph that's thrown in at the end of this section that we've been talking about, which is about the derivative using the definition with the limit. And that one little paragraph is about something that's actually fairly important, but we're not going to make a big deal out of it for now. It's what they call the higher derivatives. This is an idea that sounds kind of stupid on the surface, but it turns out to be quite useful in all kinds of applications of calculus. So the idea behind higher derivatives is we can take the derivative of the derivative. Right? It's true. We can take the derivative of the derivative. You know, if you start off with a function, you take the derivative, you get another function. I don't know if anybody ever wondered, could I just take the derivative again if I wanted to? The answer is sure, you can. You will get yet another function, all right? That other function you get is referred to as the second derivative, and it's written like this. The derivative of the derivative is that. F with two primes, and we call this f double prime. I don't know why nobody says prime prime. It's always called double prime. F double prime, this is the derivative of the derivative. It's the derivative of f prime of x, right? F prime of x is the derivative. F double prime is the derivative of the derivative. And these are called, well, in this context, this is referred to as the second derivative. The second because you get it by doing the derivative twice. And if you want to distinguish this from the other one, this, when you're talking about higher derivatives, this is referred to as the first derivative. Also known as just the derivative. But all the derivatives we've ever done have been the first derivative. You just take the derivative of a function. You can take the derivative again, and you get the second derivative. What does it mean in sort of in a real-world problem? Well, the first derivative tells you how fast the original function is changing. The second derivative tells you how fast the changing is changing. It's sort of it is a measurement of how quickly f prime is changing. All right, the change of the change, which sounds sort of too convoluted to ever be useful, but actually it is quite useful. Let me just do a sort of abstract example first of all. And then we'll talk about just very simply an example where this is actually useful for something. How about in this function here, 5 plus 2x minus x squared. Your job is find the second derivative, all right? Unfortunately, there is no sort of shortcut to do two derivatives at once. The only way to find the second derivative really is to find the derivative first, and then take the derivative again of that. Now, without using the tricks, this is a bit of a pain, but it's not so bad. So actually, this example here is one of the examples I had you guys try out last time. So would you mind if I just refresh our memory? So this was an example from last time. If you do the derivative in this example, you get f prime of x is 2 minus 2x. We actually went through all the details for that. I mean, that is basically just like the one that you did on the quiz, although not plugging a specific value and just leaving the variable. Okay? Now that we know that, how do you find the second derivative? So, f double prime of x is the derivative of that, right? It's the derivative of that one. So let's do it, and I am maybe for the last time, going to use that definition with the limit. It is the second derivative. It's the derivative of f prime of x. So I'm going to say lim h goes to 0. It's f prime of x plus h minus f prime of x divided by h, right? I'm using the old definition of the derivative, only I'm putting f primes because this time the function I want the derivative of actually is f prime. I want the derivative of f prime. So let's do it one last time. Don't shed a tear. This is the last time you use this limit definition. F prime of x plus h means I go up here and I replace x with x plus h. All right, can do that. 2 minus 2 x plus h. right? And then I go minus f prime of x, just like it is 2 minus 2x. All of this divided by h. And then we go and cancel stuff as usual. Distribute the 2 there, also distribute the minus sign. It's going to be 2 minus 2x minus 2h minus 2 plus 2x over h. And now several of these will cancel. I got a 2 and a minus 2, a minus 2x and a plus 2x. All that's left over is 2h over h. And this is 2, right? The h's cancel. There's no h left at all. So the limit just gives you 2. Okay? This is the second derivative of that function. There, like I said, unfortunately, there is no trick for doing 2 derivatives at once. And I really mean there isn't, like, this isn't something that we're going to talk about eventually. Yes? Did I mess it up? Oh, yeah, it's a negative 2. Thank you. Negative 2h. Yes, you're right. Sorry about that. Negative 2h. Gives me negative 2 as the answer. Yes, as I should have known by looking at this, because I know the awesome tricks. I am a master of the tricks. It's because I wrote on my paper plus 2. Should be minus 2. Sorry about that. All right. What is the meaning of this? The second derivative, like I said, it actually has an important meaning in lots of applications of the derivative. I think it's easiest to describe in the context of physics of motion. So if s of t is the position of some object moving around over time, then s prime of t represents, anyone remember this? This would be how fast the position is changing. Yeah, that's what they call the velocity. How fast the position is changing is just like how fast the thing is going, right? What then, how would we interpret, I meant to say then how would we interpret s double prime of t? This would be how fast the velocity is changing. We also have a common word for that. What do you think? Yeah, that's the acceleration. How fast the velocity is changing, all right? And of course, acceleration is a useful thing in the real world. So this is the classic example where people care about the second derivative. It represents acceleration in physics. Of course, you don't have to stop at the second derivative. You could keep on, take the derivative as much as you want. Actually, there is a meaning for this. The third derivative, less useful than the acceleration, but it does come up every so often. Anybody heard of this before? This would be a measurement of how fast the acceleration is changing, right? It's the rate of change of the acceleration. Anybody heard of that? There's a name for this. This is called, I'm not making this up, this is called the jerk. It's called the jerk because everybody knows when you, like as a human being, you can't really feel velocity. Like if you're inside a car that's going 60 miles per hour, you sitting in your seat still feel as though you're at rest in your immediate surroundings. You can feel acceleration though. When the car accelerates, you sort of do that, right? And when it decelerates, you do that. Now, what if the acceleration is changing rapidly, like going really fast from accelerating to decelerating? You will do this, right? Because the acceleration is changing quickly. That causes your poor body to jerk around. That's why it's called jerk, because it makes things jerk. Yeah, jerk is like whiplash is an injury caused by excessive jerk on the body. It's when like you don't really hit anything, but your head goes back and forth really fast. That's caused by jerk. Acceleration by itself is usually not very harmful, but jerk is quite harmful to people. All right, I also encountered the second derivative once. I remember once when I was in college. When I was in college, every year the tuition, like the amount we had to pay, would increase every year, and I think it does that here also. I remember one year when I was in college, we all got a letter sometime in the spring saying, like, this is what the tuition's going to be next year. And they said, unfortunately, as always, we had to increase the tuition for next year. Now, this increase actually would be expressed as a derivative because it's the amount that the tuition is changing. But anyway, the letter said we have to increase the tuition, but we have good news, and that is that the rate of increase has decreased. So they're making a statement about the second derivative there. They're saying, yeah, we know it's bad that the tuition is increasing, but the increasing itself has slowed down from last year. They were trying to make us feel good by saying something about the second derivative. I guess it made me feel a little bit good. I don't know. So these are uses of the higher derivatives. The higher derivatives are also they come about in finance too. Like if you think about it, people care in finance about interest rates. The interest you can think of, or like inflation. That's what I meant to say, which is inflation. You can think of as some kind of derivative because the inflation describes how the value of money is changing. If there's a lot of inflation, that means that each individual dollar kind of got less valuable. So inflation you could think of as a first derivative, a derivative of the value of money. And then people all the time talk about inflation rates are increasing or decreasing. They would be talking about the second derivative of the value of money. So these things, they do occur in the real world. It's not just people trying to play games with formulas. All right. Just one last thing to say about these higher derivatives. Usually we're going to write them using just like lots of primes, 2 primes or 3 primes. If you have more than 3 primes, typically people don't like to write them. So usually we go, F prime and then F double prime, F triple prime. After a while, people don't like to write lots and lots of primes because they're hard to read. So after that, people tend to write them this way, sort of a number in parentheses. So F with a little 4 up there in parentheses means the 4th derivative. The parentheses are there to make it so that it doesn't look like F to the 4th power, which is something completely different, but etc. All right? Remember, there was also this other way of writing the derivative, which is in terms of things like this. So if you want to write the derivative that way, d over dx of f, and we are often going to write the derivative like that, how you indicate the higher derivatives are somewhat strange, but it's like this. I'll write it and then I'll try to explain why. D squared dx squared. And then the next one would be d cubed dx cubed of f. So this is the second derivative, and it's written that way because this is the derivative of f, right? And so people just sort of jam together those two things that look like fractions. It's not really a fraction. It's just the way that we write the derivative. But this notation here comes from slamming together these two things as if they were fractions. I got 2 d's up top and 2 dx's on the bottom. That's why it's written this way. It's a little strange in my opinion, but usually not confusing. And then the third way that we sometimes write the derivative is this way. dy dx, that's the first derivative if y is f of x. The second derivative, if you want to write it in this style, is similarly weird. d squared y dx squared. This always struck me as very strange. Why is the squared in the top on the d, but on the bottom it's next to the x? Well, it's because of this. It's basically using this style of notation, but you use a y up top. And there's only one y, there's not 2 y's, so you don't square the y. Very strange in my opinion, but the third derivative written in this style is like this: d cubed y dx cubed, etc. All right, so this is just notations here. You might see these in the homeworks or whatever. We are mostly just going to use this style up here, but if you see some weird stuff like this, they mean the higher derivatives. All right, any thoughts about that? We're not going to say much more about the higher derivatives at this point, but we will, they'll come up every so often. All right, great. Let's move it on to the next section, the next section is about the tricks. Finally. It turns out finding derivatives of ordinary functions, I'll say of common functions, can be very easy if you know some tricks. Some basic tricks. And essentially, from now on, we are never again going to use the definition of the derivative in terms of limits. Instead, we're going to spend the next couple times basically memorizing a bunch of tricks. And I know I don't really like memorizing stuff in general, but really it's not going to be, this is not a lot to memorize, you'll see. And we're going to, the tricks are so useful that you won't even feel the burden of memorization, because it's like a million times better than using the definition with the limit. All right. In particular, so functions which we will be able to do by using the tricks, this would include all polynomials, which may get to the full trick of polynomials today. We'll see. Any trig functions, sine, cosine, tangent, etc. And also any combination of these. So any product, quotient, or composition of these. All right. Oh, I forgot to mention radicals. All right. Those will be able. We have tricks for those too. Basically, any function that you know the name of, there's probably a trick to take the derivative of it, which falls into the general sort of bag of tricks that we're going to be talking about over the next few times. Very powerful stuff, these tricks are. I think these tricks, may, you might say that like calculus is a body of knowledge which in many ways enabled the modern world to function, right? Like people created lots of science and technology using calculus. If human beings never figured out calculus, it's hard to imagine that we could have built the world as we know it today. I would say our ability to do calculus comfortably is really enabled by these tricks. If we didn't have these tricks, then calculus would be much, much harder than it is. So you could say these tricks are sort of responsible for the development of civilization as we know it. Anyway, let's talk about, so we're going to kind of build things up slowly to get to all increasingly more complicated functions. Let's talk about the simplest functions that there is, constant functions. All of the tricks will be based on figuring out the derivative of some very simple form of a function and then realizing that you can apply that derivative over and over again in other contexts. So first, the first basic form of a function I want to talk about is a constant function. That is a function that just looks like f of x equals c. All right, where c is any number. Could be 0 if you want. F of x equals c means I always get the same answer. No matter what you plug into the function, you always get the same answer, and that answer is c, whatever that number is. Okay? Can we say what is the derivative of such a function? So the derivative of f of x, then this is, what would it be? Now, I'm going to use, because we don't know the trick yet, we have to use the limit at least once to figure out what this is. And then we'll just memorize the answer and use the same answer every time we ever see a constant. That's the idea. Did I say we were never going to do this again? I meant we got to do it once here, and then we memorize the answer. So we are going to do it like once a few more times. Anyway, it's f, as usual, f of x plus h minus f of x over h. Okay, now I plug in. My function this time is f of x equals c. The answer is always c, no matter what you plug in. Can anyone tell me? Shout it out if you like. What is f of x plus h here? This here is my function, and I want to plug in, instead of x, plug in x plus h. What's the answer going to be? Somebody say C? Yeah, the answer is C. Just C. I tried to prime you with this, I said a moment ago. F of x equals C. That means no matter what you plug in, the answer is always C. So if I plug in f of x plus h, it doesn't matter. I get C. C is the answer to f of anything. So this is C. Minus f of x, well, it says right there, f of x equals C. So this is C. Divided by h. And what is that? 0. Yeah. C minus C, that's 0 in the numerator of the fraction. So I just get 0. Okay, are you capable of memorizing this? So this means the derivative of a constant function is 0. All right, this is the first of your tricks. The derivative of a constant is 0. Easy enough to memorize this rule. All right, I will write it this way. Derivative of C is 0. All right, I'll put that in a box. Everything I put in a box today, you should memorize these things without a problem. All right, that was the easiest one. Any thoughts about that? Okay, let's talk about a power of x. All right, how about I'm referring to something like f of x equal x to the n, where n is a positive. We'll get to negative powers eventually, but for now, let's just talk about positive whole number. We will also get to fractional exponents, but for now, let's just deal with an exponent which is a positive whole number. Okay, I guess we gotta do that. So I'm gonna try and do this using the definition of the derivative. Actually, just as a little warm up here, this one's a little tricky. Although once you get to the answer, it's a fairly simple answer that you get, but the process to get there is a little tricky. Just as a warm up, let's try x to the 4. I'm gonna go, so the derivative of x to the 4 is, then h goes to 0. It's going to be x plus h to the 4 minus x plus h, sorry, just, not x plus h, x to the 4, right? This is f of x plus h minus f of x divided by h. And now how are we going to find this limit? Unfortunately, we're going to have to expand out x plus h to the power 4. If that was a power 2, you just do the FOIL. Power 4 means you could actually multiply that thing by itself like 4 times. Any masters of doing that? Anybody? I was hoping at least one of you learned. There's actually a trick for doing that. Doing x plus, this is called a binomial expansion. Anybody ever thought about this? Check it out. Like this one we do all the time. If you square it, what you get is x squared plus 2xh plus h squared. Oops. If you cube it, just because I know the trick, it's this. Anybody seen this before? There's actually a pattern to those numbers. You know? Yeah? All right. Do you remember the pattern? No. There's a very cute little pattern. This is somewhat obscure and it doesn't come up very often. Anybody know? Anybody know what the numbers are for 4? I'll tell you. See if you can recognize the pattern. Sorry, that's not a 6. It's a 4. X cubed h plus, this one's a 6. X squared h squared plus 4. X h cubed plus h to the 4. Remember this? I don't know, maybe not. This is these numbers that you get in here. They're called the binomial coefficients. So for the third power, you get, it's like a 1, a 3, a 3, a 1, right? And for the fourth power, you get a 1, a 4, a 6, a 4, a 1. These numbers, you can get them from what's called Pascal's triangle. You make this cute little triangular array of numbers. And the way you get each row is by adding together the 2 numbers above it. So you always put a 1 at the beginning and at the end. And then to get each other number, you add together. So this position right here comes from adding 1 plus 4, and you get 5. The next one is a 10, then another 10, then a 5. And it turns out, like, these are the coefficients if you were to expand x plus h to the power 5. All right? I don't really want to get into why this works. It's a mysterious thing. This is called Pascal's triangle. Pascal is a French mathematician and mathematician and theologian in like the, I don't know, 1700s maybe 16. Pascal was not the one who first studied this, but as you know, things in mathematics tend to be named after the first white person who wrote about them. And this Pascal's triangle was studied by, I think it first appeared in some Arabic writings. But anyway, I'm here to tell you, this right here, x plus h to the 4, it expands out like that. This is a little shortcut so that I don't actually have to multiply the whole thing out by itself. So, by itself 4 times. So this thing, oh, I'm going to get fancy here. I think I am. Duplicate. Yes. Look at that. I expand on the top, right? It's all of this stuff. X to the 4 plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the 4. All right, that was x plus h to the 4. And then minus x to the 4 all over h. All right, what cancels? Up top, x to the 4 cancels and nothing else. But you will notice all the other things up there have a h in them, so I can factor the h out the way we always do. Let's do that. Pull the h out to the front. What remains is 4x cubed plus 6x squared h plus 4x h squared plus h cubed divided by h. We cancel these two h's and then plug in h equals 0. It causes everything in there to become 0 except for 4x cubed because all the other ones have h's on them. So after I plug, I'll just write that one last step here. 4x cubed plus 6, sorry, I meant to plug in 4x cubed plus 6x squared times 0 plus 4x times 0 squared plus 0 cubed. All right, anyway, the whole thing gives me 4x cubed. All right, this was the warm-up with x to the power 4. I will just summarize. The derivative of x to the power 4 is 4x cubed. Right. I would like us to think about where, because we want to do this generally for x to the n, not just x to the 4. Think about where exactly did this 4 come from? Well, I would say, I mean, when you look through all this nonsense, that 4 came from here, which came from here, which came from here. The fact that this is a 4 right there is really because this row in the Pascal's triangle began with a 4, right? That's where this 4 ultimately came from. And then everything else went away because it had extra h's when I plugged in with the limit. All right, anyway, let's try and do this for x to the power n. Derivative of x to the power n, all right? It's going to look pretty much the same, only the 4 is going to be an n, and I guess, I mean, some other stuff will change a little bit. Anyway, we begin the same way. Lim h goes to 0 of x plus h to the n minus x to the n divided by h. This is the definition of the derivative. Just like I did before, but I'm using n rather than 4. And the first step is the hardest. We're going to have to expand x plus h to the n. And so, to read the coefficients on that, I go down in Pascal's triangle, P's triangle. Row n looks like, remember, to get these numbers here, I read across row 4 of the Pascal's triangle. In this case, I want row n. Anyone tell me what the row begins with? Even if you're not all that familiar with Pascal's triangle, you can tell me what does row n start with? A 1. I see some fingers. Yeah. 1. And then what? Yeah. N. Yeah, the next number will be n. After that, it's kind of who knows. Like you would have had to know what the previous row looked like, but I would just say, huh? Eventually, it's going to have an n and a 1 at the end, though, right? That's how the Pascal's triangle works. It turns out, lucky for us, we don't actually need to know those numbers in the middle. The only one that matters is that n at the beginning. So anyway, when I expand this, I get x to the n plus n, x to the n minus 1h, plus a bunch of stuff which I actually don't know what it's going to look like. But eventually, at the end, we'll end up with h to the n as the last one, all right? This is expanding the thing using the Pascal's triangle. I don't actually know what most of those numbers are going to be, but I know at the very beginning we get 1x to the n, and then we get n times x to the n minus 1. All right, then, that was just the expansion. Then I get minus x to the n over h. And from now on, everything is going to work just the same as it did before. So this, the x to the n's will cancel. And then everything up top has a h on it. And so I can factor the h out. It says h on the front, n x to the n minus 1, plus a whole bunch of stuff I don't really know. And I guess h to the n minus 1 over there, because I factored out one of the h's. This is a little weird. It's pretty much over now, though. It's divided by h, of course. And let me just say, all these dots, which I don't really know what the numbers are, but all of these have I want to say extra factors of h. Because inside these dots, what you have is those coefficient numbers and then increasing powers of h. Even though I factored one of them out, this one doesn't have any h on it, but all the rest of them, they still do have more h's on them. All right? And so what's going to happen? I cancel these h's, and then I take the limit as h goes to 0, and everything up here becomes 0 except for the very first one, because all the other ones have h's on them. All right? So what I get after canceling those, it's going to look like lim h goes to 0, n x to the n minus 1 plus a whole bunch of stuff here. All of that stuff has factors of h on it. And so it's all going to become 0 when I plug the h equals 0 in. And I just end up with n x to the n minus 1. All right. This is what it all comes down to. And this is why, this is the famous power rule. The derivative of x to the power n is n x to the n minus 1. This is the most important of all the awesome tricks that we're gonna talk about. This one we're gonna use, I would say, probably every day for the rest of the semester. At least every class period. You may not use it on the weekends, but you don't go to the same clubs I do, right? This is the power rule. Super important. The power rule. All right? This is the rule about the derivative of the power of x. Any thoughts about that one? It has a weird derivation. You know, all that stuff that I just went through is a little strange. You got to use the Pascal's triangle, whatever. You don't actually have to think about any of that when you use the power rule, though. All right? All you got to do is you bring the exponent down in the front as a coefficient, and then you decrease the exponent by 1. So, for example, do some very simple examples here. What is the derivative of x to the power 6? The answer is 6x to the 5. All right? You have to, I would say, I mean, you can memorize this formula, but really, I don't really think of this in terms of the formula. The way I think about this is this 6, which is living upstairs, when I take the derivative, it comes down front, and then the 6 decreases to a 5. All right? That's how it works when you take the derivative of a power of x. So, derivative of x to the 4 would be 4x cubed, which is that's the answer we got when we did it the long way. Derivative of, x to the 1,000 would be 1,000, x to the 999, right? This is how the power rule works. It's just that simple. This one would be a true nightmare to do using the definition of with the limit. Although if you know the Pascal's triangle, it's not so bad. All right, one very special case, important special case, would be a derivative of x, like just x, to the power 1. What is this? Well, you can use the power rule to get this. You think of this as being x to the power 1. So I will say this is x to the 1. And when I do the power rule, what's it going to look like? You bring the exponent down as a coefficient, and then you decrease the power by 1. So what would it be? 1. They're all saying 1. Yeah, it'd be 1, really, to belabor the point, it would be 1 times x to the 0, right? You bring the exponent down front as a coefficient, and you decrease the exponent by 1. But x to the 0 is 1. That's because anything to the 0 power is 1. So this is just 1. All right, so this is, if you like, you could memorize that. I would suggest you just remember this sort of separately, even though it is a consequence of the power rule. So the power rule really is how you know that the derivative of x is 1. But it comes up often enough that it's worth remembering just as a special case. The derivative of x is always 1. All right? Most important formulas in mathematics, you can if you search on Google, you can find people with math tattoos, have math formulas tattooed onto them. I don't have any math tats, but the power rule is so important and so extremely awesome in terms of how much work it saves you. I looked today to see if I could find any pictures of this tattooed on somebody, and I couldn't find any. I think maybe it just doesn't look cool enough. It doesn't look all that fancy. People with math tats, they want to see they want to see infinities and pies and integral signs or the summation sign. Those look cool. I've never seen somebody with this as a tattoo. It just doesn't look all that great. Maybe try it out. Let me know if you get that as a math tat. I don't necessarily recommend it. Okay, what do we got? We got 15 minutes left. Let's talk about, so we have so far talked about powers of x and constants, all right? Really what I would like to get us to for today is any polynomial. Now, a polynomial involves powers of x's with constant coefficients. So let's talk about coefficients. What happens in the derivative? What I want to do is something like this. What happens in the derivative to that constant? I would like some kind of answer which somehow involves f prime of x, the derivative of f, right? Maybe I'll write it just because I use the d's on that side. I'll use the d's over here. The question is, when I take the derivative that had a constant in front here, what happens to that constant over here? Does it disappear completely? Does it just stay where it is, but outside the derivative? Does it, add, does it increase by 1 or what? This is what I want to talk about. All right, so let's see if we can do that. I'm just going to use the definition with the limit as always, and then see if we can maybe simplify anything. When I'm using the function c times f of x, when I plug x plus h, it looks like c f of x plus h. And then I go minus the original function, which is c f of x, divided by h, right? This is the derivative of c f of x. And now I want to know, can I somehow see what happens with that c? Can we simplify or do anything? Anyone want to suggest, can we do anything to that? To rewrite it in a nice way? Yeah. Yeah, factor out the c. The c factors out of the top of that fraction, and in fact, I can just write it like this. C times the fraction, right? F of x plus h minus f of x over h. Factored it out of the numerator. And then this is a limit of two things multiplied together. I guess I should write it that way technically, now since I factored it out. It's the limit of the whole thing. But remember, our rules for limits said If you have a limit of a constant times something, that's the same as factoring the constant out of the limit. So this is the same as this. F of f plus h minus f of x divided by h. All right? And that limit is the derivative of f. So what I end up with is c times the derivative f of x. All right? So as an answer to my question, what happens when you take the derivative of c times something? You get some stuff here. Where does the c go? The answer is the c just goes to the outside. The c can be factored through a derivative. So I'm going to write that as our next big rule here. The derivative of constant times f of x is the same as a constant times the derivative of f of x. I don't know if that looks useful. This is extremely useful. It's so useful that, like, if you know the tricks already, you might have even forgot about this one, even though you do it all the time. You don't even really think about it because it's so deeply embedded in how you do the derivative. For example, if I wanted to do the derivative of 8x to the 4, using the rule, so I already know the derivative of x to the 4. It's just a question about, like, what effect does that 8 have? Using the rule that I wrote at the top there, I should put this in a box. It means I can pull the 8 through the derivative and just make it like that. And then I already know the derivative of x to the 4 is 3x cubed. So this is 8 times 3x to the 4. What? 4, I said it wrong. 4x cubed. 4x cubed. And I guess the 8 times 4 will be 32. So that's the answer, all right? You can factor a constant through the derivative operator. Okay, now usually we don't actually think it through in these steps. I wrote all of these steps out, but ordinarily I would not write so many steps out. Really, the way to think about this is I can jump all the way to the answer just by imagining, okay, what happens to 8x to the 4? The 4, which is living upstairs in the exponent, comes down to the front and multiplies onto the 8. I get 32 in the front. And then the exponent decreases by 1, and I get 3. So this is the way that I think this through. I suppose if you want, you could think through all of that, but we're going to do this so many times that it's better to just think of the exponent comes down and multiplies onto the coefficient. All right? Any thoughts about that? Great. We got 10 minutes. We can go all the way to polynomials. So let me just say, now we can do, using these tricks, anything like, 2x to the 7 or negative 3x to the 4, etc., right? These are certain types of polynomials, but really a polynomial is a bigger thing which has a bunch of those added together, right? Those are monomials, but a polynomial is a bunch of those things added together. So what we want is, something like 2x to the 7 plus 3x to the 4. Like, what exactly does the plus do to the derivative? That's the question. And so our next rule is going to be about adding, addition, and subtraction. The subtraction rule is really just the same as the addition rule. Might as well do them both. Addition and subtraction. That's what that says there. Subtraction. Let's just do addition, and then I'll just tell you what the answer is for subtraction. It should be obvious enough, but my question is, what happens when you take the derivative of f plus g? Two functions added together, you take the derivative. How is this related to the derivative of f and the derivative of g? There should be some relationship. Let's just try it out. So when I do the derivative of f of x plus g of x, using, as usual, we have to use the limit just one last time. It's going to be, my usual fraction here with h on the bottom. Up top, what we do first, we plug in x plus h. It's going to say, so I go here, right? This function, I replace x by x plus h. It looks like f of x plus h plus g of x plus h. Right? That's what you get when you plug x plus h. Oh, sorry. You plug x plus h in here for x. All right, then I go minus 1. And then just whatever this says already as is, it will be f of x plus g of x. All right? And how can we simplify that? You know, in the previous example, we were able to factor the constant all the way out of everything. Here, you can't really factor anything all the way out, but you can rearrange things so that the f's go together and the g's go together. That will involve distributing the minus sign, and then, like I said, change the order around so that the f's go together and the g's go together. I get f of x plus h minus f of x. I move that f of x to the beginning. And then plus g of x plus h minus g of x, like so. Everything divided by h. And this, just because I know what I'm doing here, I know it's going to be helpful to split the fraction into two pieces. So I'm going to break it up into two fractions, one which just has the f's, and then the second one which just has the g's. Right? And now this is a limit of two things separately. But we got rule, you know, there was a limit rule about this. The limit of two things added together is each of the two limits separately added together. So I go, this is the same as lim h goes to 0, f of x plus h minus f of x over h. And then separately, the limit of the g's. G of x plus h minus g of x over h. And can anyone say, what are those two limits going to be? This should look familiar. What is the limit of this thing? This is similar to like the last step that we did up here. We ended up with c times that, and then this limit is the derivative of f of x. So what are these guys going to be? Too late in the day to ask questions like this? Yes. This is the derivative of f, right? That's what that limit is. I mean, I'm not looking for like a specific answer here. That is the derivative of f of x. And this one is the derivative of g of x. All right? So, what it says, this is what we started with. The derivative of two things added together, it is equal to the sum of the two derivatives. That's the point here. The derivative of f of x plus g of x equals derivative f of x plus derivative g of x. Right? This is the rule for adding derivatives. And would you mind if I just tell you, it's the same for subtracting. You can go through those details again if you wanted to. With a minus sign instead of a plus sign, nothing weird happens. It all works out exactly the same way. So it is also true that derivative f of x minus g of x is derivative f of x minus derivative g of x. All right? Put that in a box too. So now, finally, for our remaining 5 minutes, we can take the derivative of an entire polynomial. Let's try it. This is the grand finale. You came back just in time. What if I want the derivative of some big polynomial like this? All right? How do we do it? First of all, this is a bunch of stuff added together, so I can split up the derivative into a bunch of little derivatives added together. So because of that rule, you can still see in the box right there, I can split this up into derivative of 5x cubed minus derivative of 7x to the 8 minus derivative of 2x minus derivative of 5, right? This is the addition rule that I just used. And now you can just go down the list here and take the derivative of each thing. And each of those things, we already know how to take the derivative of. Someone want to shout it out? What's the derivative of 5x cubed? 15x squared, yes. They've been waiting all semester for me to accept such an answer. I accept it gratefully. 15x squared. All right? Remember the way you do this is the exponent comes down to the front, multiplies by the coefficient. So the 3 times 5 gives me the 15, and then you decrease the exponent by 1, and you get the 2 there. Okay, what's the next one? 56x to the 7, I think is exactly what he said. These are hard multiplications to do. Yeah, you multiply, the 8 comes down, multiplies by the 7, and then the exponent decreases. I think 7 times 8 is 56. I think that's right. I'm no expert in 7 times 8. But. What about this one? 2x. What do you think? 2, they say. Yeah, remember, the x by itself becomes a 1 when you take the derivative. And the 2 as a coefficient just stays like it is. And then finally, the derivative of 5 is 0, right? That was another thing. That was the first thing we talked about. The derivative of a constant is just 0. All right? Now, I wrote this out in 2 steps. So that's the answer. Well, really, you don't have to write the 0. I would expect you to just say this. Right? I wrote it out in a few steps, but really, once you get used to doing this, I would expect you to just read this across and immediately say this answer. So all you got to do is go down the line here. Each time you do the power rule and multiply onto the coefficient. So the 3 comes down here, makes 15 in front, decrease the 3, and you get a 2. And so on. You don't really need to write all these intermediate steps. In fact, you basically never will write the intermediate steps. You can if you want to, but they are not terribly helpful. You might as well skip them. All right. I had another big example to do, but I think maybe we can just leave it at that for now. Hope you all have a good weekend. See you next time.